Welcome back to the classroom. This is Mr. Wong speaking. We are going to be going through another physics exam question. This is going to be on Module 5, question 18 from the additional sample paper. This is on advanced mechanics, and we're going to be focusing on escape velocity. So let's look into the question. A bullet is fired vertically from the surface of Mars at the escape velocity of Mars. Okay, so that's satellite 1. And then we have another bullet which is fired vertically from the surface of Earth and at the escape velocity of Earth. So we call that satellite number 2. Neglecting air resistance, compare the energy transformations of the two bullets. So when we talk about comparison, we want to look at any differences and for any similarities. That's what we're trying to figure out when we're talking about comparing. Okay, that's the word we're looking into. I'll just get rid of that. I'll highlight this bit. Okay, so what can we talk about in terms of energy transformations? Well, if we're talking about transformations of objects going into space, we're looking at the total energy. Obviously, that's conserved in the case of where things are in orbit. We have the potential energy, and we have the gravitational potential, kinetic energy and gravitational potential energy. Okay. In this case, the total energy is going to be conserved for both bullets, or so to speak, it is going to stay constant. The reason being is because as we launch the bullet, there is no additional engine that's going to be placed onto it. When it comes to things like the kinetic energy and the gravitational potential energy of the bullet, we might want to just demonstrate by drawing the diagram. So we have the planet and we fire the bullet off. If we can imagine, bullet fires off in whatever orientation we want it to. Okay, so that's what we have. Now we have two formulas to describe kinetic energy and gravitational potential energy of this bullet. So the equation for gravitational potential is this one here. And the formula for kinetic energy is this one that we have here. Okay. As the bullet leaves the Earth, gravitational potential is going to increase, and what we can say is kinetic energy will continue to decrease. That's kind of what we can say. Okay. We can also measure this in terms of the distances between where the bullet is and towards the center of the Earth. As we increase our distance here of r between the bullet, that's going to take our gravitational potential energy closer towards 0 as the distance goes towards infinity. Which is what we want, which is what we'll see, which is why we say it increases, because as we go from a negative value towards 0, we're actually increasing the gravitational potential energy. Whereas as r is going towards infinity here, all right, we also find that the kinetic energy will move towards 0. As we see there. So that's actually where the similarities between the two bullets will be. We will see a conversion or transformation from kinetic energy to gravitational potential as the bullet goes further and further away from the Earth. There's your similarities. Now the next thing we can talk about is obviously their differences. What will be different is not so much the energy transformation component here, we know it's going to transform that and that. But it has to do with their escape velocity. So the formula for escape velocity is v equals to gm, or root gm r, should be 2 here. Let me just rewrite that. So square root of 2gm over r, that's escape velocity. Okay, and obviously there will be a different escape velocity for the bullet on the Earth and Mars, because the mass of the Earth, or the radius of the Earth, is different to the mass or the radius of the star. So mass of Earth is not equal to the mass of Mars, nor is its radius. So we don't expect the escape velocity on Earth to be equal to the escape velocity on Mars. That's what we can sort of tell from this here at the very least. Okay, so there's that. So what that would also imply is the subsequent quantity of kinetic energy the bullet has as it leaves the planet, and how much gravitational potential energy is transformed at the same distance away from the planet will also differ. So we will see a transformation from kinetic to gravitational potential, but the quantity of how much the actual values are for a given distance will be different. Okay, so that's what we see here. That's just a nice little summary pictorial for you. Now we will actually try and write this in proper wording. So I'm going to take this all out. And now we are going to try and write a response for this. So if we're doing comparison, like we said, we can talk about the similarities and we can talk about the differences. So let's just firstly look at where the similarities lie. Okay, we can firstly say, as both are just launched projectiles, there is no additional energy added to the bullet, and so we know for sure that the total energy will remain constant. Okay, so as there is no additional energy added to the bullet, the total energy remains constant. What we will also see is, due to the conservation law, so the law of conservation of energy, right? The bullet will convert from kinetic energy to gravitational potential as it leaves the Earth, or as it leaves the planets. We could even write down the formula, so we know that the energy total is given by kinetic energy plus gravitational potential, which is given by the following formulas. Okay, so the kinetic energy will convert to the gravitational potential. Leaves the planet. So as r goes to infinity, we expect that the kinetic energy will equal to 0. Now the reason why it goes to 0 is this kinetic energy is used to escape the or overcome the gravitational force of Mars and Earth. So the reason why it's used up all that energy is to overcome the gravitational force. So to overcome, or we can say has overcome the gravitational force of the planet. So as that goes to infinity, that goes to 0, and also gravitational potential also goes to 0. However, in this case, we are actually seeing a decrease in kinetic energy, and we're actually seeing an increase in gravitational potential from where it originally began. Okay, so it goes down, gravitational potential energy has gone up. Next we need to look at is the differences, and I will just write it in our little subheading around here, and we'll go from there. So the escape velocity formula, escape velocity will be different for the two bullets. So we know that the formula for escape velocity is 2gm over r. Okay, and what we do know is that the mass of Earth is not equal to the mass of Mars, nor is the overall radius of the Earth equal to the radius of Mars. Okay, so that's part of it, and as a consequence, we'll know that the overall kinetic energy, or the magnitude of the kinetic energy and the gravitational potential energy, will not be the same. Okay, therefore the magnitude of the kinetic energy and gravitational potential energy of the two bullets will not be the same for a given value at r. Okay, because the masses of the planets or the escape velocities in which they leave are not the same, we will not be expecting that the kinetic energy or the gravitational potential, the values for those being the same at a given distance that we discussed based on those formulas above. Okay, so that concludes this question here. Let's quickly zoom out. So that's our response comparing the similarities and the differences. If you found this video useful in explaining how the kinetic energy and gravitational potential transformations occur for same bullets at different planets, hit that like button and subscribe if you haven't done so already. We will also go through some other questions related to advanced mechanics. But until next time, thank you for listening to now, and I will see you next time.